In this video, we'll look at transition matrices in Similarity. So the last section, we looked at how to find the matrix representation of a linear transformation, but we saw that depending on which basis you choose for your vector space, you could have different matrix representations. Right, so the goal of this section is to see how those different representations are related. So if we look back at the last example in section 6.3, we looked at this linear transformation. Right, so t of xy is given by this transformation, and if we take the standard basis for R2, then the matrix representation, you can just read off the coefficients here, right? So 2, -12, and then 1, -5. Right, so that's the standard matrix representation with the standard basis. However, right, so if you go back and look at what we calculated for a non-standard basis, right, so in the calculation here where we take this non-standard basis B prime, we calculated this matrix representation A prime. Right, so we have two different matrix representations for the same linear transformation, depending on which basis we choose, right? So the standard basis gives us this representation, and this non-standard basis gives us this matrix representation. Okay, so you can see that if you compare the matrices A prime has a simpler form than A, right? Because it's a diagonal matrix. And so we want to know how to obtain the matrix A prime from the matrix A, right? So how are these two matrices related? So if you go back to section 4.7, we discussed transition matrices where you change from one basis to another, right? So the notation there was that P is the transition matrix from B prime to B, and P inverse is the transition matrix from B to B prime. Okay, so the relationship is going to be as follows, right? So A prime as a transformation takes coordinate vectors for B prime and transforms them to coordinate vectors for B prime, right? So the A prime represents the transform T working in basis B prime, right? So when you think of it as a transformation, you have to apply it to coordinate vectors of this form. Okay, so if we want to see how it's related to the matrix A, right, so the matrix A works in the basis B, the standard basis B, right? So if I want to take as an input vectors in the basis B prime, I first have to transition from B prime to B by matrix P, and then now I'm working in basis B, so then I'm allowed to transform using A, which outputs a vector in basis B, and then if I want to output in basis B prime, I need to transition back from B to B prime, right? So in terms of the order that matrices are applied to a vector on the left, you read it from right to left, right? So the matrix P is applied first to this vector, and then the output of that is transformed by A, and then the output of that is transformed by P inverse. So the ordering of things should be read from right to left. Right, so again, you want to take as input vectors, coordinate vectors for B prime. So you have to change from basis from B prime to B, transform working in basis B by A, and then transform back to B prime. And then so the effect of this should be the same as the effect of this. Right, and so we get that A prime is equal to P inverse AP by using the transition matrices. Okay, so let's see this in action with our two matrices and A prime here. Right, so we want to check with the example above. Right, so say I want to find the matrix P. Right, so P is the transition matrix from B prime to B. So if you go back to section 4.7, what you do is you set up the augmented matrix. So the augmented matrix for finding P would be to put basis B on the left and then B prime on the right. And so if we write this out, right, so I take the basis vectors in B, which is the standard basis, and I write them as column vectors. Right, so that's just 1, 0, and 0, 1. And then B prime as column vectors would be 4, 1, and 3, 1. And then the procedure was to do the row reduced echelon form. And so you should get the, I mean, this is already in row reduced echelon form, right? Because this is the identity matrix on the left. Right, to the, after doing row reduced echelon form, you get the identity matrix on the left, and then P on the right. So this is our matrix P. And so you should notice that in the situation where B is the standard basis, the matrix P can be obtained by just taking the basis vectors for B prime. Okay, so now I have my matrix P. Right, so what is P inverse? So we can just calculate that, right? So determinant is 4 minus 3, which is 1. And then this becomes a 1, this becomes a 4, and then this is a minus 3, a minus 1. Okay, so then now I want to check that this is the same as A prime. Right, so I calculate P inverse AP. So 1, negative 3, negative 1, 4 times A, which was 2, negative 12, 1, negative 5. And then P, which is this, 4, 3, 1, 1. Okay, so now let's do the calculation. So first multiplying these two matrices. What's the result of that? So that's 2 minus 3 is negative 1. Negative 12 plus 15 is 3. Negative 2 plus 4 is 2. 12 minus 20 is negative 8. And this one stays the same. And then now I multiply to get the final result. So negative 4 plus 3 is negative 1. Negative 3 plus 3 is 0. 8 minus 8 is 0. And 6 minus 8 is negative 2. And if you compare it to A prime, well, I have a negative 1 here. Oh, I miscalculated, right? So that's negative 4 plus 3, which is a negative 1. Okay, so this is equal to A prime, and so it checks out, right? So we really do get P inverse A. P is equal to A prime. We now look at a 3x3 example where we don't know what the resulting matrix A prime is going to be. Okay, so this is the linear transformation, and we want to find the matrix A prime for t relative to this basis B prime. So we're going to do it following what we did previously, where we first use the standard matrix and then do the change of basis to figure out what A prime is going to be. Okay, so first, what is the standard matrix? So this is for the standard basis, right? So I can just read off the coefficients of the variables in how the formula is written, right? So for the first component, it's 1x plus 0y plus 0z. So it's 1, 0, 0. And the second component is 1x plus 2y plus 0z. So 1, 2, 0. Then the third component is 1x plus 1y plus 3z. Okay, so that's the standard matrix. Okay, so now what we need is the change of basis matrix, P, right? So from the discussion previously, right? So the starting basis B is the standard basis, right? So since B is the standard basis, so finding P is very easy, right? So the transition matrix P is just given by the vectors in B prime. So the first column is V1, which is 1, negative 1, 0. Second column is V2, which is 0, 0, 1. And then third column is V3, which is 0, 1, negative 1. No, put it on the edge of the page here. Okay, so this is the transition matrix P, and then to save time, I put the matrix into the graphing calculator and then calculated P inverse this way. So this is P inverse, and then now we can calculate A prime. That's P inverse A P, So bring it out, it'll be 1, 1, 1, 0, 1, 1, 0, 1, 0 times A, which is 1, 1, 1, 0, 2, 1, 0, 0, 3 times P, which is 1, 1, 0, 0, 0, 1, 0, 1, minus 1. And then I'll run out of space here. Okay, so we multiply the three matrices together. But again, to save time, I've calculated it beforehand on the graphing calculator. Okay, so this is our matrix A prime. So you can verify this calculation by multiplying the matrices by hand. Okay, so so the process of determining the matrix A prime is fairly straightforward, right? So you can get the standard matrix typically by just reading off the coefficients on how the linear transformation is set up. And then again, because the starting basis is the standard, starting basis B is the standard basis, the matrix P, it can be obtained by just taking the basis vectors as column vectors. And then from there, P inverse is just calculating the inverse of P. And then A prime is just calculated as doing this matrix multiplication. Okay. So this situation where you have two matrices A prime and A related by the matrix multiplication in this exact setup where you have the matrix P and you calculate as P inverse AP. So this relationship is called a similarity transformation, right? So two matrices A and A prime related in exactly this way are said to be similar to each other. And so this similarity relationship between two matrices is in fact an equivalence relation, right? Which means it satisfies these three particular properties. So the similarity relationship is reflexive, right? So any matrix is similar to itself. It's also symmetric, right? So if A is similar to B, then B is similar to back to A. And then it's transitive, right? So if A is similar to B and B is similar to C, then A is similar to C. So we have that this is an equivalence relation. So it's actually not too hard to see why these three properties have to be true, right? So property 1 follows because, right, so to show a similarity relationship, what you have to do is you have to find the matrix P where this equation works out, right? So A is similar to A. I need to write A is equal to this matrix multiplication for A. So I need to find a matrix P where this is true. But I can take P to be the identity matrix, right? Because the inverse of the identity matrix is just the identity matrix, and the identity matrix multiplied by any matrix is itself, right? So the right hand side just multiplies out to be the matrix A. So this shows the similarity relationship for A to itself. Okay, so that's property 1, and then property 2 follows because if A is similar to B, then that means that A is equal to P inverse BP, right? Because if A is similar to B, then we have to have this equation for between A and B. Then I can turn around and solve for B in terms of A, right? So by multiplying on the left by P, right, so you get PA is equal to P times P inverse BP. Right, so if you remember, when we do matrix multiplication, whether you multiply on the right or whether you multiply on the left, you have to make it consistent, right? So here P is both multiplied on the left, and then P times P inverse is the identity matrix, so that cancels out. So we have P times A is equal to B times P, and then now I multiply on the right, right? So this is equal to B times P, and then now I can multiply on the right by P inverse. So P inverse on the right, P inverse on the right, and then this cancels out, and then so B is equal to, so I'm going to write P as P inverse, right? Because the inverse of the inverse is just the original matrix. And so this shows that B is similar to A, right? Because P inverse is playing the role of P here. Okay, so this shows the symmetric property. And then property 3, you can try to prove it along similar lines, right? So if A is similar to B, then you have this relationship between A and B. If B is similar to C, then you have this relationship between B and C, and then you have to try to construct the relationship between A and C. So I don't have any space left, so I'm not going to write it here, but you can try to figure out how to construct this yourself. Okay, so in this example, we're given two matrices A and A prime, and we want to show that they're similar to each other. So in general, if you're only given the two matrices A and A prime, and you want to see if they're similar or not, that's somewhat difficult, right? So to make things a little bit easier, you're also given the matrix P. And so basically now to show A and A prime are similar to each other, we just need to carry out the matrix multiplication, P inverse A, P, right? So since P is given to us, we can easily calculate P inverse. So P inverse is 1 over the determinant. So what is the determinant? It's -2 minus a -1, so that becomes -1. And then I switch these two, right? So 2 minus 1, this becomes, then minus 1 becomes +1, this becomes -1. So what do we get as P inverse? So this is -1, so -2, -1, 1, 1. Okay, so now we just have to carry out the matrix multiplication, P inverse AP. So written it out, what is it? So -2, -1, 1, 1. A is this. And P is this. And then we just have to verify this is the same as A prime. Okay, so let's do the multiplication. So what is this? This is -24 plus 20 is -4. -14 plus 11 is -3. 12 minus 20 is -8. 7 minus 11 is -4. Okay, and then now this one wasn't multiplied yet. And then now we calculate this multiplication. So 4 minus 3 is 1. 4 minus 6 is -2. 8 minus 4 is 4, and 8 minus 8 is 0. And then we check this is exactly the same as A prime, and so that means that A and A prime are similar. Okay, so part of the reason for the discussion of similarity transformations here is that the goal of the next chapter is going to be to determine when a matrix is similar to a diagonal matrix, and if it is similar to a diagonal matrix, how to construct that similarity by finding the transition matrix P. Right. So the reason for that we're interested in finding similarity to a diagonal matrix is because calculations involving diagonal matrices are very simple, and so by changing the basis so that we can represent something with a diagonal matrix, it simplifies various different calculations.